Welcome back to the class on a power semiconductor drive. In this lecture, we are going to discuss about the synchronous motor, construction, and expression for the power and torque developed in synchronous motor. So first, we are going to see the construction of the synchronous motor. It is also consisting of stator winding as well as rotor winding. The stator of a synchronous motor is similar to the induction motor. It is a stator core. In the stator core, the three-phase winding is displaced 120 degrees mutually in a space. For the stator winding, we are giving a three-phase supply. So whenever we are giving a three-phase supply to the stator winding, the rotating flux will be creating from the stator winding. When you come to the rotor, on the rotor, the field winding is placed. There are two types of rotors are there. One is the cylindrical type synchronous motor. This type of rotors are used for high power rating. The rotor is cylindrical structure. The surface is slotted to house the field winding. This winding is connected to the two slip ring. On the two slip ring, the brushes are placed. Through the brushes, we are giving a DC supply to the field winding. So when we are going to give the excitation to the field winding means after reaching the rotor speed is equal to the synchronous. So by means of a prime mover, first of all you have to run the rotor in the same direction of the stator flux. The speed near to the synchronous speed of a stator flux. At that time, you have to give the excitation to the field winding. So from the field winding also the flux is creating. There is a magnetic locking between the rotor flux and the stator. So the rotor also will be running with the same speed of a stator flux. That's why we are calling this motor as a synchronous motor. Generally, the damper windings are placed in a rotor. Whenever you are giving a three-phase supply, the rotor will be rotating as like an induction motor by means of a damper winding. Once the rotor speed is near to the synchronous speed, then we are going to give the excitation to the field winding so that the rotor will be pulled into the synchronous speed of a stator. In that case, no need to use the external prime mover. Actually, this type of construction is a very robust construction, but we are using this type of construction for the high power rating. Silent pole type synchronous motor. This type of construction we are using only for the middle power rating of a synchronous motor. Moreover, this type of construction also we are using where the rotor speed is very low because it has a projected force. On the projected force, again the field winding is there. The field winding is connected to the slip ring. On the slip ring, brushes are there. Through the brushes, we are giving a DC supply to the field winding. Less robust one compared to the cylindrical type of the synchronous motor. In case of permanent magnet synchronous motor, we are keeping a permanent magnets on the rotor. So no need to give the excitation to the field winding. The losses in a field winding will be reducing. The efficiency of the motor also will be more. It is designed only for the low power range. Cylindrical rotor wounded field winding is also nothing but a non-silent pole synchronous motor. This is the equivalent circuit of a non-silent pole synchronous motor. This is the per phase voltage. This is the synchronous reactance of the stator winding. This is the voltage induced in stator winding due to the air gap flux. That's why you're calling it E. This voltage will be lagged this voltage by some angle that is nothing but load angle. See here minus stands for the lag. Now we are going to find out how much power is developed in a cylindrical type synchronous motor. The power input to the motor is equal to 3 into V into IS into cos phi. V is nothing but a voltage applied to the this equivalent circuit. IS is nothing but current passing in the circuit. Cos phi is nothing but a power factor of the synchronous motor. This phi is nothing but a angle between the voltage current passing through the stator winding. If we neglect the stator losses, then the power developed equal to the power input to the motor. That is equal to 3 Vs Is cos phi. From this circuit, the source current equal to this voltage minus this voltage divided by this reactance. So V at angle 0 minus V at angle minus delta divided by Jxs. Now we are simplifying this one. Is equal to V by Xs minus pi by 2 because J is operator which is giving a phase displacement of 90 degrees minus E by Xs at angle minus pi by 2 plus delta. This is the expression for the current passing through this circuit. Now we will find the cause of this current. Is cos pi that is equal to V by Xs cos pi by 2 minus E by Xs cos pi by 2 plus delta. This is equal to E by Xs sin delta. Now substitute the equation 2 in equation 1. We are getting the power developed Pm equal to 3 EV by Xs sine delta. This is the mechanical power developed in a synchronous motor. Now this value divided by the synchronous speed of a motor that gives the torque. The torque developed in synchronous motor T equal to 3 into EV by XS omega ms sine delta. See, in this manner, you can easily find out how much is the torque developed in a synchronous motor where the rotor is a cylindrical structure and a torque also we can find out. Now if we come to the silent pole synchronous motor, where we cannot take the synchronous reactance is a constant value because it is consisting a projected pole. So this is the structure of a silent pole synchronous motor. So whenever you are giving a field winding, there is a locking between the stator flux and rotor flux. Both stator flux and rotor structure and rotor flux also will be rotating at a same speed, that is a synchronous speed. That's why we're calling this motor for the synchronous motor. Synchronous is nothing but a constant speed motor. Now we are going to see the characteristics of a synchronous motor. On the x-axis we have taken the torque, on the y-axis we have taken the speed of a synchronous motor. As the torque is increasing on the synchronous motor, the angle between the stator flux and the rotor flux will be increasing, but the speed of the motor is constant. This is the speed of a motor is constant. This is the maximum torque developed in the motoring mode. Minus P maximum is nothing but a braking operation. This is motoring operation. This is the braking operation. Suppose if you apply the load on a synchronous motor such a way that it is more than the maximum torque developed in induction motor means by the time there is a loss of synchronism between the stator flux and the rotor structure as well as the rotor. In case of silent pole wounded field winding motor, we cannot take the synchronous reactance of the stator winding is a constant. So this machine is analyzed by taking the two axes. One is the D axis, another one is the Q axis. So this is the phasor of E, nothing but the voltage induced in stator winding due to the air gap flux. This is the Q axis. The perpendicular to the Q axis is nothing but the G axis. The current lags E by some angle, that is pi. Now this stator current can be resolved into the two currents. One is the D axis current and Q axis current. The D axis current is denoted by ISD. The Q axis current is denoted by ISQ. Now we are adding the reactance drop during the D axis ISD into XSD. Next we are adding the reactance drop due to the Q axis component ISQ and XSQ. We find the phasor sum of the three vectors, that is given the V, nothing but a voltage applied to the stator winding. The angle between voltage V and E is nothing but a delta. This is the phasor diagram of a silent pole synchronous motor. From this phasor, V cos delta, nothing but the projection of V on this vector, V cos delta, minus E gives the IS into XS. Now divide by that quantity divided by XSC, that is nothing but IS, nothing but direct axis current. From this triangle, V sin delta equal to ISQ into XSQ. Quadrature axis current ISQ equal to V sin delta by XSQ, where XSQ are the synchronous reactance in the direct axis and quadrature axis of a. Now from the phasor diagram, IS cos pi equal to ISQ cos delta minus ISD sin delta. Already we derived the expression for the ISQ and ISD. We substitute those two values here. See, if we simplify means we are getting the IS cos pi equal to E sin delta by XSD plus V XSD minus XSQ divided by 2 XSD XSQ into sin 2 delta. Now we have to multiply throughout this equation by V and 3 also. Then it is given the mechanical power developed in an induction motor PM equal to 3 into EV sin delta by X XSD plus V square XSD minus XSQ by 2 XXD XSQ into sin 2 delta. Now divide this quantity by the angular velocity of a stator flux that gives the torque developed in induction motor. So finally we are getting 3 omega ms into EV sin delta by XSD plus V square XSD minus XSQ by 2 XSD XSQ into sin 2 delta. This is the expression for the torque developed in a synchronous motor where The field winding is placed on the projected pole. There is a lot of difference between the torque developed in a synchronous motor with a cylindrical structure and silent pole rotor. So thank you very much. If you have any doubt, you can ask me directly or you can ask in comment box of my YouTube channel so that I am always welcome to answer all your